Hello everyone and welcome back to the C++ 3D game tutorial series. In this third episode, we will see how to create the swap chain, which will allow us to manage multiple buffers for rendering and presenting frames to the screen. As always, we will face three main parts: the requirements, design, and implementation of all the necessary components to create the swap chain. Let's start with the requirements. We need a C++ IDE. In this series, we use Visual Studio 2022 Community. The target platform is Windows. The target graphics API is DirectX 11. And last but not least, a good understanding of the C++ programming language is recommended. Now we can start the design part. In the previous episode, we learned how to start building our graphics engine. We also initialized the Direct3D 11 graphics API. In addition, we created a logger to print useful messages and integrated it across the subsystems of our engine using the dependency injection pattern and the dependency aggregation strategy. This time, we will focus on implementing the swap chain. A swap chain is essentially a collection of buffers used for rendering a frame and presenting the frame to the screen. Think of it as a rotating queue of canvases. While one is being displayed, the next one is being drawn behind the scenes. But what do we mean by buffer? We mean a block of GPU memory used to store image data, specifically the pixels that make up a frame to be displayed on the screen. The image data stored in a swap chain buffer is essentially an array of pixels, where each pixel holds color information, the final color value resulting from all our rendering operations for that frame. More specifically, each pixel typically contains the following components: red, green, blue, and alpha, which represents transparency or opacity. There are two types of buffers involved here: the back buffer and the front buffer. The back buffer is the one we are free to render into. It is not currently shown on the screen. The front buffer, instead, is the one presented to the screen. It's called swap chain because these buffers are continuously swapped. Let's break down what actually happens. When we create the swap chain, we define how many buffers we want, in this case 3. All these buffers are stored in a circular queue. At any given time, only one buffer is shown on the screen, and this is considered the front buffer. The remaining buffers are back buffers waiting to be rendered into. At some point, we render our 2D or 3D scene into the current back buffer. Then, when we call swapChain present function, the current back buffer in the queue becomes the front buffer, and the current front buffer moves to the back of the queue, becoming a back buffer again. This cycle continues each frame. We can imagine this like a pad of paper. On each page, the artist draws a slightly different version of the scene. When we flip through the pages quickly, the image appears animated. This technique, where we work with three buffers, two back buffers, and one front buffer, is known as triple buffering. It helps reduce tearing, stuttering, and other visual artifacts. If we only have two buffers, one back buffer and one front buffer, then we are using double buffering. To keep things simple and easier to understand, this example assumes we are using full screen mode. In window with mode, things become a bit trickier since the desktop window manager DWM is involved. We will dive deeper into how that works in the implementation section. The swap chain is a key software component in any rendering engine, responsible for managing how rendered frames are presented to the screen. It decouples rendering from presentation, which is essential for efficient, smooth graphics rendering. Let's see how to introduce it in our DX3D engine. Since the render system is the software component responsible for managing the graphics API and handling its resources, we will give it the role of creating the swap chain. To allow the render system to create not only the swap chain, but also other future graphics resources provided by the graphics API, we will make use of the factory design pattern. The factory pattern is a creational design pattern that provides a way to create objects without specifying their exact class types directly. Instead of creating instances manually using makeUnique, makeShared, or similar functions, we let a factory class or method handle the creation. In this case, we will delegate the responsibility of resource creation to the render system, treating it as a factory for all graphics related resources. In practice, for the swap chain, we will add a method to our render system called createSwapChain, which will allow us to create a swap chain in a quick and simple way. If you have any questions, doubts, or comments about this topic, feel free to leave them in the comments section of this video or on our Discord server. You can find the link to the Discord server in the video description. Also, if you find these tutorials helpful, please consider supporting their development on Patreon. Every contribution makes the difference, no matter the amount. Great, we have gathered all the necessary information to start the implementation. The very first thing we need to do is simplify and improve the way we log messages and throw exceptions by using handy macros. As a first thing, let's go to the Win32 Windows C++ file. Here, let's copy the code snippet that allows us to log a message and throw an exception. Once we have that, we can head over the logger header file. Here, we will start creating a macro using the define preprocessor directive. In C++, define is a preprocessor directive used to create macros. It tells the compiler to replace all the instances of a specific name with a value or code snippet before actual compilation begins. Let's give our macro a meaningful name. We will call it the x3d log error and throw. We can also define parameters for it. In this case, we will define a message parameter to pass to both the log method and the exception. With that done, let's paste the copied code snippet under the macro definition. Since we are creating a multi-line macro, we need to use a backslash at the end of each line, except the last, to tell the preprocessor that the macro continues on the next line. Now we are ready to replace the hard-coded strings with the message parameter. Next, let's create another handy macro. Let's call it the x3d log error. As the name suggests, this macro will simply log an error message. To do this, we can reuse the log method code we used earlier. Now, let's enhance our dx3d log error and throw macro by reusing the dx3d log error macro within it. Pay attention here. We should place the enumeration values in parentheses to avoid any unexpected behavior during macro expansion. Alright, now we can use our new macros in the Win32 Windows C++ file and across all other classes in our engine. We can also use our macro in the render system C++ file. an important note here. We could simply replace what is under the field with the log error and throw exception macro. The problem, though, is that working with the Direct3D11 API generally involves checking an H result value. That's fine for a few calls, but if we need to handle many API calls this way, it can become cumbersome and less flexible. To solve this issue, let's create a suitable macro. We will start by creating a graphics log utis header file inside the graphics module. Next, let's add the DX3D namespace. With that in place, let's create a macro called DX3D graphics log error and throw. We will design our macro so that we can pass any Direct3D11 function call as the first parameter and an error message string as the second. Let's now copy the code used to handle errors from the random system C++ file. We will replace the API call with a variable named HR, commonly used to store HResult values. Be sure to wrap HR in parentheses to prevent issues during macro expansion. Also, let's replace the error entry snippet with the macro we just created. Here, an important thing. Make sure to pass res to the failed macro and not the original function call, otherwise we would end up calling the API function twice. Cool, now we can use our new macro in the render system C++ file. As we can see, the code is much cleaner and easier to read. Let's finally test our program. As expected, the program throws an exception during Direct3D initialization. What we need to do now is finish creating other useful macros like loginfo and logwarning, which are identical to the log error macro we created earlier. Once that's done, let's use loginfo in the game C++ file. Alright, everything seems to be working well. We are now ready to start creating the swap chain. As first step, let's go to the render system C++ file and call the query interface method on the ID3D11 device. Query interface is a core method used to ask an object if it supports a specific interface, and if so, to retrieve a pointer to that interface. To do this, we also need to use another ND macro called IIDPPVArgs. This macro automatically provides the correct interface ID and safely casts the output pointer when calling a function like query interface. At this point, what we need to do is access the DXGI device. So let's go to the render system header file and add a com pointer to the DXGI device. Next, we need to create a swap chain. To do this, we must obtain the DXGI factory, which, as the name suggests, allows us to create various DXGI related resources, including swap chains. The actual hierarchy looks like the one on the screen. So, after calling query interface on D3D11 device, we now have access to the entry point of the XGI, the XGI device. From here, we need to call the getParent method to obtain the XGI adapter, which represents the GPU selected during the 3D11 create device. In this case, the primary GPU. Then we call getParent again on the adapter to get the DXGI factory. As we can see, the factory gives us full control to create any swap chains we need. Alright, now we can dive into the creation of the swap chain class. Let's remember to place all our graphics resources inside the source branch of the project. As usual, let's wrap our class in the DX3D namespace. We will also inherit from the base class and mark our class as final. Now we can implement the constructor. In this case, we don't need to define a destructor manually. Inside the constructor, we can finally call the createSwapChain method. Always remember that we are following the RAII idiom, so initialization logic should go inside the constructor, and any necessary cleanup should be placed in the destructor. Cool, what's next? Of course, we need to access the DXGI factory somehow, and we should get it from the render system. The idea is to always adopt the dependency injection design pattern, and in particular, constructor injection, to pass dependencies across the various parts of our engine in a clean and scalable way. In this case, we can create another base class for graphics resources, which we will simply call graphics resource. This class will provide core Dir3D components like Dir3D device and the DXGI factory to all render system related resources, such as the swap chain and many other resources we will implement throughout the series. So let's start by creating the graphics resource header file. As usual, let's wrap everything inside the DX3D namespace. At this point, we can define the graphics resource class and make it inherit from the base class. Let's also implement its constructor. With that done, we can add some protected attributes. In other words, attributes that can only be accessed by derived classes, but not externally. In particular, let's add a non-null reference to the D3D11 device. Let's also include the D3D11 header file to get all the D3D11 API definitions. Next, let's add a non-null reference to the DXGI factory. Alright, with this we now have the foundational Diri3D11 components needed to create all other render system resources. Now we need to initialize the various attributes using the member initializer list. Let's start by calling the base class constructor, then proceed with initializing the D3D device and the XGI factory references. To pass these dependencies into the graphics resource, let's follow the dependency aggregation strategy and create a graphics resource descriptor structure. As first thing, let's add a base descriptor as the base of the structure. Then, we will add non-null references to the D3D11 device and the XGI factory. Once that's ready, we can define the graphics resource descriptor as a const reference parameter in the graphics resource constructor. Finally, we can complete the member initializer list and mark the constructor as explicit. Alright, we are now ready to go to the swapchain header file and make swapchain inherit from the graphics resource class. Of course, we also need to add the graphics resource descriptor as a non-null custom parameter to the swapchain constructor. Now we are ready to implement the initialization of the swap chain. Let's call the graphics resource constructor in the member initializer list. At this point, we can finally use the DXGI factory reference and call the createSwapChain method. As with many other DirectX functions, we need to pass several parameters. The first one is the device, which is of type IUnknown. It's defined this way because the function can accept multiple types of devices, not just the 3D11 device, but also others. Let's go ahead and pass our D3D11 device reference. The second parameter is the address of a swap chain descriptor, so let's create it. As usual, let's initialize it using curly braces. Now we need to set a series of values. First, we should define the attributes of the back buffers used internally by the swap chain. Essentially, the canvas where the graphics will be rendered. It's like the surface an artist draws on. For this canvas, we need to set the width, which should match the width of the client area of our window. To retrieve this value, let's adopt the dependency aggregation strategy again. So let's go to the common header file and start creating the swap chain descriptor. To provide the size of the client area to the swap chain, we should create a suitable class called rect, which stands for rectangle. Let's create a module called math, where we will place all math-related classes. Inside it, we can start by creating the rect header file. Once that's done, as usual, let's add the DX3D namespace. Now we can start defining the rect class. This class should be quite simple. First, let's define a default constructor. A default constructor is a parameterless constructor with an empty body. However, for clarity, we can use the equal default keyword to explicitly mark it as a default constructor. At this point, we can define its attributes. Before going further, let's go to the core header file and simplify some basic types. By using the using keyword, we can create type aliases. For instance, E32 to represent a 32-bit integer. Here, 32 means 32 bits, since an integer is typically 4 bytes that are 32 bits. Of course, we can do the same for other types like float, double, and more. Alright, now let's define the rect attributes. Since we want to represent attributes like left, top, width, and height in pixel coordinates, the most suitable type to use is integer. As always, let's use curly braces to initialize them. What's next? We can define some helper constructors to easily create our rect instances. For example, we can define a constructor that only takes width and height, defaulting left and top to 0. Then we can define another constructor that allows us to set all four attributes. So far so good, we are now ready to complete the swap chain descriptor. The first attribute we need to define is the handle to our window. Then we will define the size of the window using our rect class. Don't forget to include the rect header file. Next, let's add this new descriptor as the first parameter of the swap chain constructor. Of course, let's rename the existing second parameter to avoid any confusion. With that completed, we now have access to all the values we need to create our swap chain. Let's proceed by passing the width of our window. Pay attention here. Create swap chain will fail if we pass zero negative values for the width or the height. To avoid this, let's use the standard max function. There is a catch though. Due to the inclusion of DirectFreed 11 and Windows headers, a max macro might already be defined, which conflicts with the standard max function. To fix this, let's go to the project properties, navigate to the C++ list, and then go to the preprocessor section. Edit the preprocessor definition field and add the no min max at the end of the list. This will disable the max macro, allowing us to safely use the standard max function. Now we can set the width as the maximum between 1 and rect width. Let's do the same for the height. We are now ready to set the color format of the canvas. Let's use this one. Here we are defining a render buffer where each pixel has 4 color channels: red, green, blue, and alpha, used for transparency or opacity control. Unorm means we are working with normalized unsigned integers. Each channel is 8 bits, and these values are normalized to a 0-1 range in the shader. This will be extremely important later in the series when we will introduce and use shaders. At this point, we need to define the buffer count. In other words, how many back buffers, in the case of window with mode, will be used before presenting to the screen. If we set our swap chain to run in window with mode, the buffer count defines only the number of back buffers. No front buffer is included here because the front buffer is represented by the desktop and is handled by Windows through the so-called Desktop Window Manager, or DWM. If we set our swap chain to run in full screen mode instead, the buffer count also includes the front buffer. Let's set the buffer count to 2. We will dive deeper into the reason for this in just a moment. These will also result in triple buffering, as we already discussed in the introduction. What's next? We need to set the buffer usage attribute. This tests the XGI how we will use the swap chain's buffers. Let's use usage render target output. This tests the XGI that we will be using the buffer as a render target. We will deepen much better the render target topic in the next tutorials. Alright, now we can finally set the output window, which needs the HWND of our window. Let's use static cast keyword to safely cast from void pointer. Next, we need to set the sample count for multisample anti-aliasing. For now, we don't need it, so we can just set it to 1. Now we have to set the swap effect. Let's use the swap effect flip discard. Flip discard is a modern swap effect where, in window with mode, the back buffer is not copied to a separate surface. Instead, it is flipped or swapped and directly handed off to the Desktop Window Manager or DWM for composition and presentation. These can be done because the back buffers created in the swap chain are shared with the DWM, allowing the system to display the content directly without needing to copy it, which leads to better performance and reduced latency. Last but not least, let's set the window width attribute to true so we can run in window width mode. We will dive deeper into full screen mode later in the series. So far so good, we can now finally pass the address of this descriptor to the create swap chain method. At this point, let's finally retrieve the output parameter, which is the DXGI swap chain. As usual, let's add a com_pointer attribute to the swap chain class and call it swap chain. We will use this to store the reference to the swap chain instance. Here, let's always remember to use our dx3d log error and throw macro, so we can properly log an error and throw an exception whenever a Direct3D API call fails. Alright, let's dive into the next step. Now, we need to create the swap chain somewhere, and that's going to be done from the render system. Let's add a create swap chain method and pass the swap chain descriptor as parameter. At this point, we need to define its return type. Since in general all resources generated by the render system can be shared across multiple components, and since each resource could potentially have multiple owners, we should start using the shared pointer. Let's go to the core header file. Shared pointer is a smart pointer that manages the lifetime of a dynamically allocated object using reference counting. Unlike unique pointer, which deletes the object as soon as it goes out of scope, shared pointer keeps track of how many pointers point to the same object. The object is only deleted when the last shared pointer is destroyed or reset. An important note here, we are defining a new type, swap chain pointer, so we don't have to write out the full definition every time we want to use a swap chain. We will do this for all the render system resources. Since we will be using these graphics resources a lot in our DX3D engine, this is super helpful. Let's finally use a swap chain pointer as the return type of the create swap chain method. Now we can go ahead and implement it. Here, we might get some errors due to a missing the X3D namespace prefix in the return type. To avoid having to write the X3D all the time, we can use the using namespace directive. Pay attention though, it's not always recommended to use using namespace, especially in header files, because it can cause name collisions, just like we saw earlier with the max macro and the standard max function. So, if you want to use using namespace, do it only inside C++ files and only when really necessary. Alright, now we can finally instantiate our swap chain by using the make shared function. Of course, don't forget to include the swap chain header file. At this point, we need to pass the graphics resource descriptor. Since this descriptor provides all the key Direct3D 11 resources available in the render system, and since these main resources will be passed to the swap chain and many other future resources, let's create an important private method called getGraphicsResourceDescriptor. This would be a convenient method that gives us the descriptor in a clean and compact way. Let's always use brace initialization. As the first attribute, we need to pass the logger. Then we need to pass a non-null reference to the D3D11 device. To do this, first call the get method to obtain the row pointer, then dereference it using the star operator to get the reference. Important note here, the logger we're passing is part of the base descriptor structure, so we will need to add an additional brace initialization block inside the graphics resource descriptor braces. This is a compact way to initialize our descriptor. If preferred, we could define each field one by one using temporary variables, but for now, let's go ahead with this approach. Lastly, let's pass the non-null reference to the DXGI factory, using the same method as we did for the D3D device. And that's it. Now we just need to call the getGraphicsResourceDescriptor method inside the makeShared function. With that completed, we can finally start creating the display class inside the game module. As usual, let's include our class inside the DX3D namespace. This class should inherit from the window class, and we should mark it as final. We can define this class as the actual game window, the place where we render all our 3D graphics. To do that, we need to define the constructor, but most importantly, we need to define the swap chain attribute, which is the core component that allows rendering in our window. Alright, let's implement the display constructor. Obviously, we need to pass a window descriptor to the base window constructor. So, let's go to the common header file and finally create the display descriptor structure. As the first attribute, we should define the window descriptor. We should also add an extra attribute inside the window descriptor, which is the size of our window. Next, we need to define the size attribute inside the window class as well. At this point, let's go to the Win32 Windows C++ file and initialize the size in the member initializer list, passing the width and height values to the RC variable. Last but not least, let's go back to the common header file and define the final attribute of the display descriptor, which is a non-null reference to the render system. This will allow us to create a swap chain from the display. We are now ready to use the display descriptor in the display constructor, and as usual, let's mark the constructor as explicit. At this point, we can finally provide a window descriptor to the base class constructor, and then create the swap chain. Here, we need to pass the handle of our window. So let's go back to the window header file and make the attributes protected, so they are accessible from the display class. Then we can also pass the size of the client area of the window. What we need to do now is go to the game header file and replace the window pointer with a display pointer. Let's remember to make a forward declaration of the display class in the core header file. So far so good. Now we have to create a display instance instead of a window instance. Since we now also need to pass the size of the window and finally a non-null reference to the render system, let's go to the graphics engine header file and add a getRenderSystem method to retrieve that reference. Since this method doesn't alter the state of the class and shouldn't throw exceptions, let's mark it as constant and no except. In the implementation, let's return the render system. When using the star operator on a unique pointer, it dereferences the internal row pointer, giving us a non-null reference. Last but not least, let's return to the game C++ file and retrieve the render system. As we can see in the game constructor, each component, like graphics engine, display, etc., clearly and explicitly exposes its dependencies. This is a direct result of using the dependency injection pattern. We are trying to avoid hiding dependencies inside other objects. For example, if we pass the graphics engine to the display instead of the render system, we will be hiding the actual dependency, the render system, which is what the display really needs. Alright, there is nothing left but to debug our program. As expected, we have reached the swap chain constructor. The create swap chain method has been successfully executed, and in the end, our window is shown as usual. As the very last step, we should pass the window size from the game constructor. So, let's go to the common header file and add a rect attribute to the game descriptor with a default value. Then let's go back to the game C++ file and pass it into the display constructor. Finally, let's go to the main C++ file and pass a custom size for the game window. What we need to do now is go to the render system C++ file and fix the create swap chain method by adding the const keyword at the end of the method. This explicitly declares the method as constant, since it doesn't alter the state of the render system. We will do the same for the getGraphicsResourceDescriptor method. Now we are going to take care of an important topic. Let's create a scope by adding two curly braces. Inside this scope, let's add a swap chain pointer. Let's remember this is a shared pointer to a swap chain instance. At this point, let's add a further nested scope inside the one we just added. Inside it, let's create a render system. Once we have a render system, let's use it to create a swap chain and let's retrieve its pointer. Since we are not passing valid parameters, the swap chain will not be created and an exception will be thrown. To avoid this, let's go to the swap chain C++ file and comment out the create swap chain method. What happens in this case? We initialize our render system and create the swap chain, but the render system goes out of scope and is deallocated before the swap chain, even though the swap chain depends on it. In particular, the swap chain depends on the 3D11 device and the XGI factory, which are both managed by the render system. So currently, we are free to use the swap chain even though the render system is no longer alive. These must absolutely be avoided. To ensure the swap chain or any resource created by the render system doesn't outlive the render system itself, we need to store a shared pointer to the render system in each resource. We can do this by adding a shared pointer in the graphics resource class. Let's start by extending render system from enable shared from this. This important class allows us to create a shared pointer from the this pointer. We will understand better how this works in a moment. For now, let's go to the graphics resource header file and add a shared pointer to a constant reference of render system in both the graphics resource descriptor and the graphics resource class. We use const here to make sure the render system cannot be modified inside its resources. At this point, let's initialize the render system pointer using the member initializer list. Now we are ready to go to the render system C++ file and pass the shared pointer to the render system from the graphics resource descriptor. Unfortunately, it is not valid to create a shared pointer by directly passing the this pointer. To solve this issue, we can use a method provided by enable shared from this called shared from this. With that completed, let's go to the graphics engine header file. We don't need to do much, just change the unique pointer to a shared pointer. It's really important to make it shared, otherwise undefined behavior could happen due to the usage of enable share from this. Of course, in the graphics engine C++ file, we also have to use the make shared function. At this point, we can start debugging our program. We will finally see that even if the scope in which the render system was created has ended, the render system is deallocated only after the swap chain, thanks to the reference counting system provided by the shared pointer. In conclusion, let's remove the temporary code snippet and uncomment the create swap chain method in swapchain C++ file. That's all for now, folks. Today we learned how to create and initialize the swapchain class. We saw how to inject the necessary resources like the 3D device and the XGI factory, which are needed to create the swapchain, by creating the graphics resource descriptor and graphics resource class. We also explored how to create useful logger macros along with the display class, which allows us to combine the window and the swap chain together. And in the end, we turned our render system into a simple factory class that cannot be destroyed before its resources are properly deallocated. In the next episode, we will dive into the creation of the device context, which will finally allow us to start rendering on the screen. I hope you enjoyed this video. See you soon. Thanks for watching.